Today's lectures are going to be a bunch of chunks with the Fourier series. We'll probably do a little bit with Fourier transforms. A lot of it's going to be in the Mathematica. The first thing I want to do is just show the connection between the way I do it and the way Boaz does it in the book. Then I'm going to highlight through the Mathematica file and a few other examples by hand just some key issues that come up with it, some key Mathematica commands. At the end of the day, the best way to get comfortable with Fourier series and Fourier transforms is to do them in Mathematica numerically, where you have the ability to plot as much as you can. It's all well and good to do the few cases. There's a couple that you can do by hand analytically, square wells, triangle wells, some simple integrals. And you can do the integral and you can get an answer, but it's hard to get an intuition unless you really do some key plotting examples. So on Thursday, we do a really important by hand example that I think really drives home intuitively what the Fourier series and what the Fourier transform is. And we'll use a little bit with the delta function. But like I said, that's the most important thing. So you'll probably, again, want Mathematica on Thursday. It'll be helpful to have it. The other thing I do, we'll just have the one problem on Thursday. It may or may not take the whole time. So there will be a lot of other time. I mean, we're kind of the test the following week on all this linear vector space stuff. So I want to leave some time on Thursday for just questions. So feel free as you finish the problem, or if you have any questions, bring them with you. You know, as you're working on the problem, you can ask me other questions on Thursday. Now, the first thing I want to do is just talk a little bit about normalization. We mentioned that sine nx, which we might indicate by ket n, is one of our orthogonal basis vectors because we know it's an eigenvector of a Hermitian operator. Again, with the ket notation, there's lots of things you can do. You can actually write the sine function inside of it. You can use just n if we all know we're dealing with sines. One of the confusions, of course, is the complete basis is sines with cosines. And I've never seen a totally complete convention. Sometimes you just use a different integer for it. You'll see in my notes and lectures, sometimes I'll actually use a little subscript, S for sine, C for cosine. When I really want to be clear, I'll just write the function inside the ket. When you do this with exponentials, the exponential itself is a complete basis, and you can just use n, and there's no ambiguity really there. But we are interested, you know, as a function, we want our basis not only to be orthogonal, but we want it to be normalized. And so we have our normalization constant, as we refer to it. And the whole point of our normalization constant, when we define our function sine n, is so that n equals 1. That's what we want. This is one of the times where you actually have to do the integral. So we actually want to integrate from minus pi to pi sine squared nx dx. And hopefully you recall the identity for sine squared. It's 1/2 1 minus cosine 2x. So if you remember, one of the few extremely useful cosine of 2x is
1/2 1 plus cosine of 2x.
No, you're confusing this. Cosine, the double angle formula itself is cosine 2x is cosine squared minus sine squared. Right? Now remember, right? You do sine of a plus b is sine, cosine, cosine, sine. Cosine is cosine, cosine. Then you clap for the minus sign, sine, sine. Right? You got to remember that little, right? So sine is sine, cosine, cosine, sine. Cosine is cosine, cosine, sine, sine. And you've got your two trig identities. You got to learn things any way you can. And once you have this, you use cosine squared plus sine squared equals 1 to replace whichever one you're not needing, and that'll give you the double angle formulas. The nice thing is, if I'm going from minus pi to pi, right, I get 1/2 x minus pi to pi minus sine 2nx over 4n from minus pi to pi, but that's just 0 because sine of 2 pi is always 0 for any integer, and I get my 2 pi over 2, or just pi. So that's what the integral of sine squared is, which I realized I have to go back and check. In one of the other lectures, I may have written it as 1 over pi yesterday. So just double check that. There might be an error. Once you have that, then I realize the integral from minus pi to pi of a squared sub n sine squared nx dx is just an squared times pi, which we want to equal to 1. So our normalization constant is 1 over the square root of pi. Couple things to notice about what we're doing. Our interval is minus pi to pi. So our periodic function is nx. If our integral, say, had been minus 1 to 1, what are we going to have here in the sine function? A pi. Otherwise, we're not period, right? Sine of minus 1 doesn't necessarily equal sine of 1, but sine of minus pi equals sine of pi. So I adjust what's in here based on what my boundaries are. And that's all part of understanding that this has to be an eigenfunction of d squared dx squared. So it has to be appropriately defined for our linear vector space, which is periodic functions on whatever interval we have. So if I have the interval from 0 to, say, 2 pi, then again I just have sine nx, because that's periodic from 0 to 2 pi. But if I have the integral from 0 to L, I need a 2 pi x over L, because that's going to make me periodic from 0 to L. I'll just write that last one down. Right, if my interval 0 is less than or x less than or equal to L, then my function that is periodic is sine 2 pi nx over L, because when x equals L, I have the sine of 2 pi n, which is what I want. So that's why, if I keep in mind that this is a linear vector space, and that's what I'm using as the eigenvectors, I don't actually have to worry too much about memorizing all these different cases. I don't have to memorize minus pi to pi, separately from 0 to 2 pi, separately from 0 to L, separately from minus L to L. They're all the same, and I just know I need to create the sine function that is periodic on that range. And the same for the cosine, and the same for the e to the ix. So having done that, we now realize that the full n is going to be that. The cosine one will be that.
Why don't we just change our inner product so that we don't have to carry these around?
Well, it turns out for Fourier series, because it's one thing you could do is put these with the dx.
Yeah.
But it's just, one, I think it's tradition.
Okay.
And two, it's one case where it's easier to assign the prefactors with the normalization and just use your inner product as f of x gx dx and keep that same metric than to assign the things with the dx. So usually there's a physical reason. So like when we do angular integrals, we put the r's with the d theta d phi, because that's giving us the right dimensions for our differential. Does that?
Yeah.
I mean, the other way to say it is these factors aren't really associated with the coordinate in any sense.
Yeah.
So it doesn't make sense to associate them with dx. They're really associated with the function. Now, the tricky one, we do have to go back and check, and we realize we do have the case of m equals 0. This is our cosine 0x, which is 1. We don't have a sine 0, because what's sine of 0? 0. So that's not meaningful. But we do have this one. And for our normalization, we're now integrating from minus pi to pi of just dx. We don't have that factor of 1/2, so we're just going to get 2 pi. So the normalization for 0 is a 1 over square root of 2 pi. And again, if you're keeping in the back of your mind that everything is eigenvectors that have to be appropriately normalized, there's nothing you have to actually memorize here, because you can just double check it each time you need to use it. Now, if you don't want to derive it every time you use it, there's some standard cases that's worth keeping in mind. But knowing where these square root of pi's and square root of 2 pi's come from help keep it, less memorizing and easier to check what's going on. So now we've developed enough machinery, we can compare what we've done here with what the book does. Are we good on this? And the notation I've been using. Now, if you go to the book and you look it up, the book will tell you that the sine-cosine Fourier series for f of x is 1/2 a0 plus a1 cosine x plus a2 cosine 2x, ... That's the cosine part of the series, plus b1 sine x plus b2 sine 2x plus ... And then the coefficients are defined as the integral of 1 over pi from minus pi to pi of f of x cosine nx dx. And bn is 1 over pi, the integral from minus pi to pi of f of x sine nx dx. So what do we want to notice that's a little bit different? First of all, they don't separate out a different a sub 0 formula. And the reason is, you have to remember there's a 1/2 here. Our 1/2, that's why I left that up, is working out because of the normalization of 0, has that 2 in with the square root of 2 pi. That's where our 1/2 will come from. The book does it by just explicitly putting it here, and then you have the a0 and the b0. Notice we have square roots of pi floating around. The book has a pi in the coefficient. This is a standard issue with Fourier series and Fourier transforms. Do I take my normalization and treat it as a real normalization and put it both with the series and the coefficients as a square root of pi? Or do I don't really worry about the fact that this is a linear vector space and a normalization, and I don't like square roots? And notice here all the functions do not have any pi's with them, and all of the pi is in the coefficient. They're arithmetically they're the same, which I'll show you in a second, but conceptually they're a little bit different. One recognizes the fullness of this being a linear vector space. The other is more a convenience of keeping the pi's in the right place. One of the things that this means is, since we all use a different convention, many packages do not normalize at all. They drop all the factors of pi so that you're free to put them in where you want. So then if you try to create series, or if you do something, particularly with Fourier transforms, where we do the transform and the inverse a lot, if you do the transform and then you do the inverse back, you should get your original function. Now, if you aren't carrying any normalization factors around, you won't. You'll be off by whatever that normalization factor is. So you have to be aware when you use a numerical package, what are the conventions it is using. Is it using this kind of convention from the book, where all the pi's are with the coefficients? Is it using our convention, where it's splitting the square root of pi's? Or is it just not bothering to normalize anything and letting you do it? Now, that's how the book would write the Fourier series. The way we would do it in our notation is simply f of x equals the sum from n equals 0 to infinity of a sub n, and I'm going to switch to my subscript c for cosine, plus b sub n, and my subscript s for sine. Where 0 is that function. The n cosine for n greater than 1 is that function. And the n sine for n greater than 1, or for n equal to 1 or greater, is that one. And to get our coefficients, we just use the inner product. And in fact, my notation is such that I could use the same inner product for an and bn, but let's be specific. We're using the sine and cosine one. Notice now how the square root of pi's work out. Our inner products have a 1 over square root of pi coming from the bra, the integral from minus pi to pi, cosine nx f of x dx. And this one has a 1 over square root of pi, again coming from the bra, minus pi to pi, sine nx dx. Notice I don't need to worry about the complex conjugate because my basis functions are real, but I have a square root of pi floating around on my kets, and I have a square root of pi floating around on my a sub n's. So when I multiply my a sub n times my ket, I get a 1 over pi, which is exactly what you get when you work it out in detail from the book. So in either case, if I don't use the shorthand of coefficients, what I have is f of x equals 1 over 2 pi times the integral from minus pi to pi of f of x dx. This is the n equals 0 term, and notice this is just the average of f. Right? The average of a function is the sum of all its things divided by the number of points, or if I'm doing it by an integral, the integral from minus pi to pi divided by b minus a, which in this case is 2 pi. So that's the average of f. And then I get a sum from n equals 1 to infinity of 1 over pi, the integral from minus pi to pi of cosine nx f of x dx times cosine nx. That's the cosine series. Using my notation or the books, that's what it is explicitly when you plug in for the a sub n. And then, of course, you have the sine piece. Now, one way to think about it is the book does not worry about a normalized basis. It has an a sub n times a sine nx. So it's just sine nx we know is not normalized, whereas we worried about a normalized basis by having the 1 over square root of pi. That's the difference. And so our a sub n has an extra 1 over square root of pi in it. This a sub n has a 1 over pi. Now, I want to highlight a key idea here. The book's method really is specific to the interval minus pi to pi in a sense, because they've explicitly written the function, they remembered that it's a 1 over pi, they did all of that. Our notation, and this is why we spent time on the bras and kets, except where I tell you what the kets are, except for that line up there, this line and the first line is independent of the interval I choose. The interval I choose tells me what ket n is. It tells me its normalization. It tells me everything. So I know it's basically a sine or a cosine of some argument, but figuring out that argument, figuring out what the normalization is, I do all once I'm told the interval. And so my formula is way more general when I use bras and kets. The final little piece Does anyone need to see this still? The final little piece, it's really cool when we do it with the exponential case. The normalization for the exponential is dividing by the square root of 2 pi. You know, it looks really simple, and we really can write our basis, reminding ourselves it's a delta function, and Cn really is just n projected onto f of x. And now, because we're really comfortable with our bras and kets, we realize we need the e to the minus inx f of x dx. And that's an easy minus sign to forget when you memorize formulas, but when you remember that the dot product gets a complex conjugate, you're not going to forget your minus sign because you'll do your complex conjugate.